Thank you, Silvia, for the introduction. And let me thank the organizer, Giovanni, and Monica, and Silvia for inviting me in this session. It is a pleasure to be here. Okay, so let me start. Sorry. Okay, it's fine. Okay, here in the blue box, you can find the system I'm interested in this talk. So the system is minus delta u equal to v to the power p minus 1 times v plus a perturbation term, a small perturbation term, epsilon alpha u plus beta 1v. This is linear in u and v. And the second component is minus delta v equal u to the power q minus 1 times u plus epsilon times another linear term in u and v. Here, omega is a smooth bounded domain in Rn, epsilon is a small parameter, alpha, beta 1, and beta 2 are real numbers, and the exponents p and q are positive and they lie on the critical hyperbola, this green hyperbola here. Okay, so this is the system I am interested in, and let me emphasize two special cases. This is the system, I'm rewriting the system. Okay, when the two exponents are equal, then the fact that the two exponents are equal and the p and q belongs to the critical hyperbola means that it means that the system reduced to this. We can assume that the system reduced to the single equation. This is in the blue box here, minus delta u equal u to the power 4 over n minus 2 times u. P equal q means that they are equal to the critical exponent. This is critical for the Sobolev embeddings. And the system reduced to the single equation here. And when q is equal 1, then p is equal to n plus 4 over n minus 4, and this in this case n is greater or equal than 5. And the system reduced to a fourth order critical equation, which is written here. So biharmonic of u equal to u to this exponent, which is critical for the embedding of the delta square. Here there is a linear perturbation term, and we have a Navier boundary condition. Okay, now I will focus on the single equation in the box, which is the equation which is equivalent to the system when p is equal to q. And let me tell you what is known about this equation. Okay, this is the famous Bredzisz-Nirenberg problem, and it is well known that the existence of solutions to this equation strongly depends on the geometry of the domain omega and on the sign of beta. Here I wrote the linear perturbation term as epsilon times beta. Epsilon is positive and beta can change sign. And indeed, this equation has no solution. These are very well known facts. I'm just reminding this result because they are useful for what I'm going to say about system. So it is well known that if the domain is star-shaped and this beta here is less or equal than 0, then the problem, the Bredzisz-Nirenberg problem, does not have any solution. And this is due to the classical Pol-Zipf identity. On the other hand, it is also well known that a positive solution to this equation exists if and only if the linear term epsilon beta is between 0 and capital lambda 1 of omega, which is capital lambda 1 of omega is the first eigenvalue of minor delta with homogeneous Dirichlet condition on the boundary. So a solution, I can find a solution if and only if this epsilon beta is between 0 and this capital lambda 1 of omega, at least when n is greater or equal than 4. Okay, now what can we say about the system? This is the system. Well, concerning the non-existent part, it is possible to show that there are no solutions if the domain is star-shaped, and this matrix here, now you see that the linear part depends on 4 numbers, alpha, beta 1, beta 2, and alpha, which can be collected in a matrix. Well, we can prove that the system does not have any solution if the domain is star-shaped, and this matrix here is negative semi-definite. Okay, this is similar to the result I just quoted about the Brzezinski-Nirenberg problem. And this can be obtained by a generalized Boltzmann identity, which is due to Puch and Servian by Mitidieri and van der Vorst. Okay, there are different steps to get this Boltzmann identity. And in particular, there are no solutions if P and Q are greater than 1, alpha is 0, and beta 1 and beta 2 are both negative. Okay, what can we say about the existence of a solution? Well, if P and Q are greater than 1, alpha is 0, and both beta 1 and beta 2 are positive, and this relation holds epsilon squared. Beta 1, beta 2 is less than the first eigenvalue of minor delta with the Dirichlet boundary condition to the square. This generalized the previous relation I wrote for the Brzezinski-Nirenberg problem. Okay, so I can find a solution if this condition in this peak box holds. Okay, this is a sort of generalization to the previous result. There are extra conditions on the dimension n, which depends on P and Q, but I will not spend many words about this fact. This is the result. This existence result is due to Ursula, Mitidieri, and van der Vorst. And what can we say about the proof of the result? Okay, the proof of the result relies on this fact. Okay, if you look at this system, alpha is 0 in their case, well, solution to this system are critical points of this functional here, of this strongly indefinite functional. Okay, now in the subcritical regime, which that is P and Q, the exponents P and Q are below the critical hyperbola, one can use an indefinite functional theorem due to Bencher-Rabinowitz, as used, for example, by Ulos and van der Vorst and by Feldman the Figueredo, or topological method, for example, used by Clement, Figueredo, Mitidieri, and Pelletier, van der Vorst, to produce a solution, a critical point of this blue function. Okay, this can be done in the subcritical regime, but in the critical regime there are more difficult, because besides a Palais-Smith condition, this approach requires compactness of the gradient of the non-quadratic part, which fails in the critical case. And it is why Ulos, Mitidieri, and van der Vorst used a dual formulation due to Clark and Deckeland. Okay, this is the proof given by Ulos, Mitidieri, and van der Vorst to produce a solution to the system. Another approach, which is in my opinion very interesting, is follows an idea due to Pierre-Louis Lyons. Indeed, he reduced the system, the red system here, to a single equation. Okay, roughly speaking, you can take V from the first equation, like to Laplacian of u to the power 1 over p, and you plug v into the second equation, what you get is an higher order single equation. Okay, if you solve this problem, then v given by this formula solve the second, the pair uv solves both the equations. Okay, so having in mind this reduction, well, one wants to find a solution to this single equation, but one can see that solutions to the equation are critical points of this energy. Okay, the energy J, which is defined in this way, and this is defined in this space. Okay, J of U, and U belongs to the space W2 times P plus 1 over P of omega intersection with W01, comma P plus 1 over P. Okay, and so if I want to find a solution to the system, it is enough to find the critical point of this energy. In the subcritical regime, when P and Q are below the critical hyperbola, this approach has been used by Denis Bonner, Emerson, Barreiro dos Santos, Miguel Ramos, and Hugo Tavares in some recent papers. Okay, now having in mind this point of view, well, the easiest critical solution one can find is a least energy solution. Indeed, it is possible to prove that J constrained on the sphere in LQ plus 1 and the unit sphere in LQ plus 1 as a minimum. So we can find a least energy positive solution to this problem. Okay, so this is similar to what the Brasileira, what we can do for the Brasileira equation. So now we have a least energy, so we have a solution to this problem, which is a least energy. So there is a function, there is a least energy solution, and what one can try to understand is the profile of this solution as epsilon goes to 0. And Ignacio Guerra in 2008 studied the asymptotic profile of this least energy solution, and what they found was the following. So U epsilon and V epsilon, which is defined in this way, remember that I used Lyon's approach to reduce the system to the single equation. So there are two components, U and V. So both components blow up at the same point, xi star in omega. And what it is important is the shape of the two components the shape of the two components around these blow up points. And if you look at the two components around the blow up point, what you see is this, what is called the bubble, U, capital U, mu xi, capital V, mu xi, which is defined in this way. Now, what is U, capital U, mu xi, capital V, mu xi? These are scaled. These are obtained by capital U and capital V by scaling and translation. And capital U, capital V, this red pair, is the unique positive radial solution to this system in the whole space Rn. Okay, so what you see is that the solution, the least energy solution around the blow up point, goes to 0 everywhere. It looks like a bubble, so it goes to 0 far away from the blow up point, and at the blow up point it goes to plus infinity, because this scaling parameter mu epsilon is going to 0, and the concentration point xc epsilon, where the solution has the maximum, goes to the point xc star. Okay, this is more or less what. Okay, without picture, it is difficult to say, but you have to think that the solutions are going to zero everywhere, except to a point where they blow up. And the profile of the blow up is given by this pair of solutions, this pair of bubbling. Now, this bubbling phenomena is very well known in the Brzezinski problem. This was discovered by Guerra for the system, but it was well known for the Brzezinski problem. Indeed, in 1991 and in 1989, Han and Ray studied the asymptotic profile of the least energy solution found by Brzezinski, and what they discovered was the following. The solution, the least energy positive solution, blows up at the point xc star in the domain omega. And if you look at the shape of the solution around the blow-up point, well, the solution looks like a bubble. What is the bubble in this case is the solution to the critical problem in the whole space Rn. Okay, so we take the radial solution to this problem. We translate in this way the maximum, and then we scale it in this way, and what we get is again a solution to this problem, and this is the shape of our least energy solution. What is important is also that the blow-up point xc star, where the solution is going on, is a critical point of the Robbins function. This is important. What is the Robbins function? Okay, the Robbins function is nothing but the regular part of the Green's function evaluated at the diagonal. I will be back to this point in a minute. Okay, so having in mind the profile of the least energy solution, knowing also the location of the blowing up point, what has been done for the Brzezinski regular problem is the construction of a bunch of positive and sign changing solution which blows up at different points in omega. And this was done using a Lyapunov-Smith procedure. So using this Lyapunov-Smith procedure, one can build a solution to the Brzezinski problem which blows up at one or more points in omega. The shape of the solution around each blow-up point is nothing but a bubble, as before. Okay, here you see the profile is around the blow-up point xi star is the bubble. Whose concentration parameter is mu I, and whose concentration point is the point xi. Here Si is +1 if the bubble is positive, if you have a positive blow-up point, and Si is -1 if you have a negative blow-up point. Okay, and what can we say about the location of these blow-up points? Well, it is well known that this construction is possible as soon as you have a stable critical point of the so-called reduced energy, which is nothing but this function, this green function in the gray box. Okay, this is a function which depends on k parameters, mu1, mu k, which are positive parameters, which correspond to the concentration parameters of the bubbles. And it depends also on k points, xi1, xk, which are the blow-up points. And the reduced energy looks in this way. So here you see this term epsilon mu I square, which comes from, oh, sorry, here there is a beta which is missed. Okay, this comes from this linear perturbation term. And this guy here RCI is the Robin function at the concentration point XCI, and the GXCI XCJ is the interaction between the two peaks have the same sign, or it is negative if they have different sign. Okay, and what is this important I would like to point out is that if k is equal 1, so it means that I'm looking for a solution with only one blow-up point, then the energy is nothing but the mu, concentration parameter, to the power n minus 2 times the Robin function at the point C minus epsilon mu square. And in order to find a solution with one blow-up point, what I need is that Xc star is a stable critical point of R. Oh, what do I mean by stable? I mean a minimum point or non-degenerate critical point, or a maximum critical point. Okay, this is a stable critical point. You can think of a non-degenerate critical point. Okay, so this is well known, and you imagine what I want to do. We ask if it is possible to build positive and sign-changing solution to the system. The system and the Bresis-Nirenberg problem share have a lot of similarities. So it is natural to ask if I can use a sort of Lyapunov-Schmidt procedure to build positive and sign-changing solution to this system when this parameter epsilon is small. That's important. The parameter epsilon has to be small. I want to find this kind of solution which blows up at different points in omega, and the shape around each blow-up point is plus or minus a bubble. And what is the bubble in this case? The bubble is the solution to the limit system. So capital U, capital V, scaled in a suitable way. And what did I do for the single equation? If you remember here, I pointed out a reduced energy. So I asked if it is possible to find a reduced energy was critical points produce a solution to the system. This is what I want to do. And the answer is yes, it is possible. It is painful, but it is possible. And this was done in collaboration with Shan-Suk Kim from the Nankai University in Korea, South Korea. Okay, let me tell you the main result we have. We have many results, but this is the easiest to put. So I am talking about a solution with only one blowing up point, one blow up point. Okay. So what we prove is the following: if epsilon is small enough, this red system has a solution which blows up at a point Xc star in the domain omega, if one of the following conditions is satisfied. Beta 1 is positive, or beta 1 is 0 and alpha is positive, or beta 1 and alpha are 0, and in that case, beta 2 is positive. Okay, in what I'm saying is P less than Q, okay? Otherwise, the role of beta 1 and beta 2 change. Okay. Moreover, the shape around the blow-up point is the bubble, and the concentration parameter mu epsilon is going to 0 as epsilon is going to 0. The concentration point Xc epsilon is approaching C star as epsilon goes to 0, and the pair mu star Xc star is a stable critical point of this reduced energy. This is similar to what I said before. Sorry, I want to come back to the case of the Disneyland problem. This is the reduced energy in the case of a single blow-up point, okay? And what we did for the system is something similar. Now, please look at there are two different reduced energy according to P. I mean, if the exponent P is close to the critical exponent, I mean, it is greater than this number, n over n minus 2, then the reduced energy is similar to the reduced energy I found for the single equation. In particular, here, the contribution of the blow-up point is the Robin function, the classical Robin function, okay? This term into the brackets is nothing but the energy related to this linear part, okay? I'm talking about energy because in order to write the energy, I use the Lyon's approach, okay? But, so this is the reduced energy when P is greater than this number. But if P is less than the number n minus 1 over n minus 2, the reduced energy is different. I mean, the term which comes from the linear perturbation is the same. But the terms which comes from the blow-up point, I mean, the point C, is not the Robin function anymore, but this is a new function, R tilde, which is new, and whose definition is quite involved, and I will be in a moment to the definition, okay? Oh, okay, please, okay, sorry. There is a gap here. You see that if P is between these two numbers, look at this box, then I don't know what can I say, because this gap is related to the regularity of R tilde, but it is technical. I don't want to go into details. Okay, a couple of comments. We give an abstract result which allows to find the blowing up solutions via the existence of critical points of reduced energy, and which gives you the location of the concentration points and the rates of concentration parameters. However, it is extremely difficult to find the critical points of the reduced energy in the general case. Here I am talking about solutions with more than one blowing up point. The previous result was about only one blow up point. Here I'm talking about solution with more than one point. And for example, if I want to look for a solution, for a sign-changing solution with one positive blow-up point and one negative blow-up point, I can write the reduced energy, but it is extremely difficult to find a critical point. And indeed, the existence of solutions with more than one blow-up point is a largely open problem. Okay, now I don't know how much, maybe I don't have many time. Let me tell you how the proof goes on. Okay, the proof relies on the finite dimensional Lyapunov-Schmidt reduction, which is extremely powerful, as you know. And the proof is based on 3 steps, okay, which are classical, but in this setting are not trivial, because we have to do we have to do a lot of work, as you can see. Okay, the first step is the first ingredient in the Lyapunov-Schmidt reduction is the non-degeneracy of the bubble. This is the first step, okay? The second step in building the solution is to find the good answers, okay? And finally, the third step is the choice of the functional space where my system is defined. Okay, a few words about the non-degeneracy. What does it mean? Okay, what we know, remember, then I will be quick on this part. remember that my bubble is a solution to this system, okay, this red system. Pierre-Louis Lyons wrote the system as the single equation, this red single equation, and found a ground state by solving this minimizing problem, this blue minimizing problem. Well, it is possible to prove, and that was done by this list of people, that the ground state is positive, radially symmetric, and unique up to dilations and translations. What does it mean? It means that all the positive solutions to the system are given by this pair of functions, which are obtained by U and V by translation and dilation. Okay, so it is clear that if I want to solve, if I want to linearize this system, I mean, I want to find the solution to this blue system, okay, for sure, I get solutions which are given by the derivative of U and V with respect to the parameter, the concentration parameter mu, and also I find that the solution which are given by the derivative with respect to the point xi. Remember that xi, the point, belongs to Rn, so I take n derivatives, and so what I get is Rn plus 1 solutions, okay? Now, what I say is that the solution is non-degenerate if all the solutions to this linear system are a linear combination of the Zi. Okay, and this is true. Okay, the question is, are the bubble non-degenerate? And the answer is yes, they are non-degenerate. And this was done in collaboration with Rupert Frank and Shanku Kim. Okay, all the solutions in this space are linear combinations. So the non-degeneracy is okay. And now the second problem, I will not give you the details of the proof because this is technical. Now, the second problem is finding a good answer. Finding a good answer. And this is difficult because in the case of a single equation, what you do, you take the bubble, you project the bubble solves the problem in the whole space. The bubble does not satisfy the Dirichlet boundary condition. So what you have to do is to project the bubble onto H10. It means that I have to solve this problem, okay? And once you solve this problem, once you take this projection, you have a perfect answer to cook your solution, okay? And this is done in the case of the single equation. Now, let me convince you why this is difficult in our case, and then I will finish my talk. In the case of the system, the linear projection does not work very well. Why? Look at the system. This is the system, the limit system, the word Rn. I rewrite the system using Lyon's idea as a non-linear equation. Okay, so what I have to do now is taking the bubble to project the bubble in order to have a Dirichlet boundary condition, because I want a solution which is 0 on the boundary. So what I have to solve is this problem. And this problem is not linear. And so if I wanted to find a good expansion of this projection, I have to work a lot. I'm sorry, but my time is over. I don't want to bother you again. I hope that I convince you that the problem, this is our result, okay? And thank you very much for being here. Okay, muito obrigada.